Hey folks, so in this video we are going to summarize um molarity in terms of how you use molarity to find how to make solutions either from a solid or by doing a process called a dilution. And if you haven't watched the first video called Introduction to Molarity, you may want to go back and look at that because that one goes over the introduction to the molarity equation and how to handle those calculations. But if you feel comfortable with that material, or you've already watched that one, then you're in the right place. So this is to go over the functional question of how, if I sent you into the lab, how would you actually make a solution, all right? So, and a solution with a particular concentration and a particular volume. So let's look at an example. So first off, this one says, describe how to make 250 milliliters of 0.1 molar NaOH beginning with solid sodium hydroxide. All right, so we're going to begin this one with the molarity equation, just like we did in the previous activity. The definition of molarity is moles of solute per liter of solvent. And we're given that we want to create a solution that is 0.1 molar, so that's going to be our M, and we need 250 mils of that. That's going to be our volume. Remember that you want to divide that by 1,000 and change that into liters before you plug it in. Okay, so we're going to do 0.1 molar. We don't know the moles, so we're going to call that X over 0.2500 liters. And then we're going to isolate X. I like to think of this as cross multiplication because I think that's easier for most folks. Effectively, you're multiplying both sides by 0.25. Whichever way you want to think about it is totally fine. So that's 0.025, and that ends up with a unit of moles. All right. And now, but you're asked to describe how you would do this in the lab, right? So you can't measure out 0.025 moles of a substance because there's no like device that does that for you, okay? So we actually need the grams of the sodium hydroxide in order to proceed. So we're going to take that 0.025 moles of NaOH, and we're going to say, all right, 1 mole of NaOH, and now we're going to go to the periodic table and add up the molar mass. Sodium is 22.99, oxygen is 16, hydrogen is 1.0. That comes out to a nice even 40.00 grams when you do that. All right, so moles cancel, we're left with grams. And so when you plug that through the calculator, that's just going to come out to be an even 1 gram, or at least that's what it is in my head. Let me just double check because inevitably I'll screw it up. Oh, no, that's right. So that's going to be 1.00 grams of sodium hydroxide. Notice that we're still not done because we're asked to describe. We're not asked how many grams, we're asked to describe. So here's how those descriptions go. You're going to weigh out, or if you're being picky, you would say mass out, but I think that's silly. So I always say weigh out 1.00 grams of solid sodium hydroxide. All right, it's these little white pellets. You'll be used to this after a couple weeks of using this in lab. Solid sodium hydroxide, and you're going to place that in a very specific piece of glassware. The piece of glassware, I'm going to draw it, but you'll see these in lab and hopefully become very familiar with them. They have kind of a wide base down here at the bottom, and then they have like a really long, skinny neck, and somewhere on that neck is a very thin line that is the exact volume corresponding to that flask. So in the lab, we have volumetric flasks of every size ranging from 10 milliliters up to 2 liters. You go to the shelf and you grab the one you need. So in this case, we're looking for a 250 milliliter flask, and this device is called a volumetric flask. And so anytime you're describing how to make a solution of a specific molarity, you're always going to be asked to describe the glassware, including, in this case, the volumetric flask. So we're going to weigh out a gram of solid sodium hydroxide. We're going to place that in a 250 milliliter volumetric flask. And then we need to add enough water so that the total solution volume is 250. So then we're going to fill to the line with DI or distilled, whatever you prefer. We use DI in our lab, with DI water. Now, notice that we're not adding 250 milliliters of water. If you add 250 milliliters of water to a gram of sodium hydroxide, you will end up with a solution volume that's not just 250, all right? It'll be a little above that. So you, and sometimes it's a little below because of weird things that happen when solids dissolve, blah, 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 blah. You don't need to worry about it. You just need to know that we don't want to add that volume of water. We want the total solution volume to be 250, not how much water is in it. So if you fill to the line with deionized water, you know that your solution, when you fill it up to that line, is going to have a total volume of 250 milliliters, which is what you're actually being asked to do. That corresponds with the molarity definition that we've been working with, which is moles of solute for liters of solution, not liters of water, not liters of whatever your solvent happens to be, liters of solution. And I can't write or spell. That should say liters of solution. Okay, so in order to make that solution volume, you fill the line with deionized water. Okay, easy peasy. All right, so now let's look at a different example. Let's see how you would make 250 milliliters of 0.1 molar NaOH, in other words, the exact same solution, but now starting from a stock solution that you're provided that's 1 molar in NaOH, all right? So if you need to work with a stock, what is a stock solution? A stock solution is just a solution that you have in stock, meaning somewhere in your chemical storeroom, and you're going to use that stock solution to make other solutions, all right? So someone has already made a 1 molar solution. You're being asked to dilute some of that to make 250 milliliters of 0.1 molar solution. All right, for this, we're going to usually use an equation, and different textbooks will have this written different ways, but I like to write this as C1V1 equals C2V2. Some textbooks use M1V1 equals M2V2. And I think it's silly because that seems to imply to people that this only works for molarity. It works for any unit you want to use. It's just that in chemistry, we only use molarity. So when you go into biology courses and they're doing weird things with like milligrams per deciliter or something, you can use the same equation. It's all the same, which is why I like to write it as C1 to emphasize that this is concentration. Okay. And so the other nice thing about this is that whatever your volume units are on one side, it's going to match the units on the other side. So you don't, unlike the molarity equation, you don't always have to be changing everything back to liters. So let's actually do this for this equation. I like to, when I'm doing this, I like to change, or I like to write these out up here. Like I like to label, okay, that's my V1 because that's in milliliters. And that volume is going to correspond to this concentration of sodium hydroxide. So that's my C1. And then my C2 is my stock solution, and I don't know what the volume is. So the volume 2 of the stock solution is my unknown. That's the thing I don't know, and that's what I'm going to be solving for. All right, so let's plug in. So we know that C1 is 0.10 molar. We know that V1 is 250 milliliters. Again, no need to change the liters. Your C2 is 1 molar. We don't know what volume of that we're looking for, so we're just going to leave that as V2. We're going to solve for V2 by dividing both sides by the 1 molar, 1.0 molar. Molar cancels. The unit you're left with is milliliters, so your volume that you're going to get when you do this calculation is going to come out in milliliters. So that's going to be 25 milliliters that you're going to get as a result of that calculation. Now again, you've been asked to describe how to make the solution. So what are you going to do? You're going to measure out 25 milliliters, and normally you would use a pipette rather than a graduate. Sometimes you have to use a graduated cylinder for logistical reasons. Here you're going to use a pipette. I'm not going to actually make you specify that, so I'm just say generically, measure out 25 milliliters of the 1.0 molar stock solution and place that in a 250 milliliter volumetric flask. There's that volumetric flask again. And we're going to do the same thing and fill to the line with deionized water. All right. So every time you make a new solution in a volumetric flask, the last step is always fills the line with deionized water. All right. No matter what. Okay. So if you are being asked to describe to make something from another solution that's of a higher concentration, this process is called doing a dilution. And to do a dilution, we're usually going to use this dilution equation, the C1V1 equals C2V2. There are other ways to do it. You could find the moles of the diluted solution and then plug that into the Molarity equation of the concentrated one and solve for volume. I find that that's a pain in the neck, so I like to do it this way. All right. So two ways to do this. Backing up, you can start with solid, all right, and use the Molarity equation to find how many grams that, or how many moles that is, and then change your moles to grams. But if you're doing a dilution from an already prepared solution that's a higher concentration, now you're going to use this dilution equation, and you're going to pipette over how much you need, and then fill the line with deionized water. All right. So I'm going to give you a practice problem here. Describe how you would make 100 milliliters of 1 molar HCl, starting with concentrated HCl. Concentrated HCl is a particular kind of hydrochloric acid that comes in these scary bottles that are 12 molar. And so in this case, when you say concentrated HCl, it's a specific molarity. You don't really care. I want you to decide which of the two processes that we've gone over in this video you need to do the calculation, and then write out how you would make it. Don't just say it to yourself, like write it out in words. And after you've done that, watch me do the solution. Okay, so pause the video and work the problem. All right, hopefully you've had a minute to solve this problem. So because you're starting from a concentrated solution, this is a dilution. So this is going to require C1V1 equals C2V2. And so we want to make 100 milliliters, so we're going to call that volume 1 of 1 molar solution. So that's C1. Notice that the ones go with each other, right? You're going to end up with 100 milliliters of 1 molar solution. So those have the same number with them. And your C2 is this concentrated one. We don't know the volume of that we need, right? That's the part we don't know. So that's our unknown. So incidentally, if you call the 1 molar C2 and the 100 V2 and the 12 C1, it all works out just the same. Some people get really hung up on that. To me, it doesn't really matter. As long as you keep the molarities and the concentrations that go together with the same number, everything works out fine. All right, so C1 is 1 molar, V1 is 100 milliliters, C2 is 12 molar, oops, 12.0, trying to be good about my sig figs here, 12.0 molar, and V2 is our unknown, so we're going to divide both sides by 12.0 molar. Molar cancels, so we're going to plug effectively 100 divided by 12 into our calculator, and we're going to get that V2 is 8 point, we got two significant digits, so we're going to say 8.3 milliliters. All right, so now how do we do this? We're going to measure 8.3 milliliters, and in the lab, I'm going to make you do this with a graduated pipette. Measure 8.3 milliliters of the hydrochloric, the 12 molar hydrochloric. By the way, I'm not going to let you mess with 12 molar hydrochloric in the lab because it's scary, but anyway. Measure 8.3 milliliters of 12.0 molar hydrochloric acid into what are we going to use? Well, we want 100 milliliters, so we're going to use a 100 milliliter volumetric flask. And then what are we going to do? We're going to do the same thing we do every time. And then we're going to fill to the line with DI water. Now, someone's going to bark at me in the comments. This is not exactly how you would do this because you actually, with acids, they're kind of dangerous when you add water to them directly. So there's this old thing about do what you oughta, add acid to water. So you actually in the lab, you actually add in a 100 milliliter volumetric flask, you would put maybe 40 or 50 milliliters of water in there to begin with. Then you would add your 8.3 milliliters of your HCl. Then you would fill to the line with deionized water. That's a detail that I don't really expect at this point of your chemistry development for you to know. When you take quantitative analysis your junior year, you'll spend a lot of time worrying about these sort of details. Again, I'm not letting you play with concentrated acids in the lab. I'm just mentioning it to you as a safety thing, and also because this is on the open internet. Maybe people are going to watch this and go in the lab and try to do it. But so if you're actually doing this in the lab, you would get your volumetric flask, and you would put a little bit of water in here to begin with, maybe 50 mils of water. Then you would add your 8.3 mils of your concentrated hydrochloric acid. Then you would fill to enough with enough deionized water to get to the line. But anyway, that's a detail I don't expect you to know for this, for the purposes of testing on this. All right. All right. I hope this has been helpful. Please leave me a comment or a question, or get in touch. And thanks for watching.